Okay, here we go. There is a formula that's going to come up in these notes. And once you know where the formula comes from, you can recreate it on your own. If you forget it, it's kind of a complicated formula, but you can recreate it on your own. But before we get to that, let's just establish a few ground rules involving inverses. And I think it's worth saying a couple things that are going to come in handy. Inverses, and these are tricky little things, inverses is where you switch variables and then solve for y. And in that case, you will have switched x and y. So I just want to come over here on the side and I want to write something that's going to come in handy. So if, this is like old school stuff that you knew, if I have some coordinate like AB, that's not an interval, it's just the coordinate AB. Oops, bumped my camera, sorry. If AB is on the graph of F, then BA is on the graph of F inverse, because inverses inherently switch x and y. All right, so knowing that, let's get started. If f equals the square root of x plus 1, which is graphed right here, this is the graph of f, then find the derivative of f inverse of x at x equals 2. So let me rephrase that a little bit. They are saying find f inverse of 2 derivative. Now they can put the derivative sign here, they can put it in a different place. But that's what they're asking, okay? They want to know the value of the derivative at 2. So what I'm going to do is kind of a roundabout way just to establish one of the ground rules for this before we get into the more complicated part. And we're going to just go ahead and find an inverse. And in order to do so, we switch x and y. This is some old school stuff right here. We switch x and y, and we will solve it for y. So we would square both sides, and we will add 1 in this case. And this is the inverse. Let's get a little more technical. This is the inverse. And not only is that the inverse, I do want to clarify that because switching x and y means we swap domain and range, then the range of this original function, being from 0 to infinity, means that the domain of the inverse is from 0 and up, 0 to infinity. So x squared plus 1 would be a parabola that extends to the left and to the right forever, but not in this case because it's an inverse. Okay, fantastic. They want to know the value of the derivative at x equals 2. All right, cool, fine. So the value of the derivative of the inverse at x equals 2. So f inverse derivative of x, and notice I put the apostrophe here, I put it here, there, it's kind of the same notation. The derivative of this would be 2x, which means to finally answer the question, if I plugged in a 2, I'd get a 4. All right, so bringing my work over here a little bit. The value of the inverse, derivatized, not a word, at 2 is 2 times 2, of course, which is 4. All right, let's make some sense of this. Here we go. I'm going to draw x squared plus 1 to the best of my ability. There it goes. And it goes to the 0.52, which means it goes to the 0.25. So I'm going to try to get that correct. There we go. So this is the inverse. This little graph that I just drew, that little guy right there is the inverse. And this graph right here is the original function. And they asked us to find the slope of this graph at that point, and we found it to be 4. So the tangent line here has a slope of 4. I didn't draw it exactly right, but the tangent line has a slope of 4. Okay? Check this out. I want you to check this out and watch it good. Watch it well. Sorry, bad grammar. The coordinate 2, 5 is on the graph of the inverse. The coordinate 5, 2 is on the graph of the original function. Okay? I wonder what the slope of the tangent line is here for the original function. So just bringing my work over here, I've answered the question. but I'm experimenting at this point. And so knowing that f is equal to the square root of x minus 1, the derivative of f is, okay, chain rule, we will take the derivative of square root, which is this, and then leave the inner part intact, multiply by the derivative of that inner part, and the derivative of that inner part is just 1. So this is truly the derivative of f, not its inverse. And so we can evaluate that same thing, not at 2, but at 5. Okay, here goes. Here's what's about to happen. I have found the answer to the question, and the answer was 4. I want to see how it compares to the slope of this line, which is the slope at its corresponding point. And it goes back to this statement. If 5, 2 is on the graph of f, then 2, 5 is on the graph of the inverse. So when I was asked to find the slope where x is 2 on the inverse, that's where y was 2 on the original function, okay? So I'm going to find that, because 2 and 5, they go together in this context. And so I would have 1 over 2, square root of 5 minus 1, which gives me 1/4. This slope is 1/4. Not drawn very well. So this slope is 1/4. This slope is 4. I would like to think there's something obvious that happens. Okay, what you just saw demonstrated was not a proof, but it was a demonstration of one example of what I'm about to write. So here we go. Derivative of an inverse function at a point. If a comma b lies, it means it doesn't tell the truth, no, I'm kidding, lies on the function, lies on, not of, lies on the function f of x, and the derivative of the function at a is just some slope, then, okay, before we finish the sentence, let's figure this out. 5, 2 was on the function, and the slope, when I plugged in a 5, was 1/4. So for its inverse, the value of the derivative at, okay, not at a, but at b, at its opposite, at what would have been its output becomes its input. At b is, okay, what was 1/4 became 4, it got reciprocated. There we go.